Hello, welcome to the course PH6B13E Computational Physics. The contents of today's lecture is taken from Numerical Methods for Scientists and Engineers by K. Shankar Rao. We will continue to discuss topics from Module 2, Numerical Methods in Physics. In the last class, we discussed about curve fitting. In today's class, we will talk about another numerical technique known as interpolation, which is very similar to the curve fitting we have discussed earlier. So once again, we have done some experiment, and from that experiment, we have made some measurements, and the experimental data points are xi, yi. For example, if you recollect the problem we discussed in the previous class, we have set of x and y values. Okay. And here we do not know the exact relationship between x and y. The only thing we know that we have done some experiment and we have got certain x and y values, and we don't know the relationship between them. So in curve fitting, what did we do? Or more specifically, in the case of straight line fit, what we did was we established a linear relation between x and y. So this is a straight line relation, y equal to mx plus c. So once we know the theoretical function connecting these two, then we generated a theoretical curve. Then we overlaid the theoretical curve with the experimental data, and then we have seen how well the theoretical curve fitted the experimental data. That is the curve fitting approach. Okay. So that is the specific case of a straight line fitting. In general, we try to find a polynomial y equal to f of x. So once you find this polynomial, for any given x point, you can calculate the corresponding y value. Okay. Now, if the x value lies within the range of observed data points, it is called interpolation. For example, here, suppose I want to find the y value corresponding to x equal to 3. So x equal to 3, this is not an experimental data, but here the x value lies within the range of the observed values, right? So once you know f of x, you substitute x equal to 3, you can find the corresponding y value. So if x lies within the range, it is known as interpolation. If x lies outside the range of observed data points, it is known as extrapolation. For example, you want to find the y value corresponding to x equal to 50. Once again, this information is not a part of the observed data or the experimental data. Once again, if you know f of x, you can substitute for x. When you put the value x equal to 15, you get the corresponding y value. So this is known as extrapolation. Now, one of the methods used for numerical interpolation is known as finite difference method. So once again, imagine that you have performed some experiment and you have obtained n data pairs x1, y1, x2, y2 all the way to x and yn, and you do not know the relation between x and y explicitly. So one thing you have to remember is that the x values are equally spaced. Like the example I have given here, the difference between any two successive x value is a constant here. Okay. So finite difference method is a method of determination of y value corresponding to a given x value within the range of data. And there are three types of finite difference: forward difference, central difference, and backward difference. And the operators associated with these methods are generally known as finite difference operator. So we are going to talk in detail about the forward difference, but I will also give you a flair of central difference as well as the backward difference. First, the forward difference. So once again, you have n number of experimental data points, and the first forward difference is defined as the difference between two successive y values. So y1 minus y0, this is the first forward difference term. The first forward difference operator is capital delta. So capital delta y0 is y1 minus y0. Similarly, y2 minus y1, this is delta y1. And y3 minus y2, this is delta y2. So same way you find all the first forward terms. Now the second forward difference, the corresponding operator is del square, and second forward difference is nothing but the difference between two successive first forward difference terms. So here the first two terms are delta y0 and delta y1. So you take the difference of these two, delta y1 minus delta y0. This is the second forward difference term, delta square y0. Now you can expand the first forward difference terms. Delta y1 is y2 minus y1. Delta y0 is y1 minus y0. So you get delta square y0 equal to y2 minus 2y1 plus y0. Similarly, you can find the next term, delta square y1. This is going to be delta y2 minus delta y1. Once again, you expand this, you get y3 minus 2y2 plus y1. Same way you can find all other seconds forward difference. Next is the third forward difference given by the operator delta cube. So third forward difference is nothing but the difference between two successive second forward difference terms. So delta cube y0 is nothing but delta square y1 minus delta square y0. So once you find the difference terms of various orders, you can compile them into a table, and this table is known as the forward difference table. So a table with given data points and all the higher order difference terms is known as difference table. So imagine you have 6 data points x0, y0, x1, y1 all the way to x5, y5. So you can construct the difference table. Let's start with the first difference terms. So you have y1 minus y0, which is delta y0, y2 minus y1, you have delta y1, similarly delta y2, delta y3, delta y4. So one thing you can note here, you have 6 number of data pairs here, but in the first forward difference you have 6 minus 1, 5 terms. Okay. So this is true for all the successive difference term. As the order of the difference term increases, the number of elements decreases by 1. So as the order increases, number of terms decreases by 1. So once you construct the first order difference, you can go to the second order difference, delta square. So delta y1 minus delta y0, this is delta square y0. Delta y2 minus delta y1, this is delta square y1. Similarly, delta square y2, delta square y3. If you look in the first forward difference, you have 5 terms. In the second forward difference, you have only 4 terms. Similarly, go to the third order difference, delta cube. Expectedly, this will have 1 term less, which is 3 elements. So delta square y1 minus delta square y0, this is delta cube y0. Similarly, delta square y2 minus delta square y1, this is delta cube y1 and delta cube y2. Moving over to the next order, delta to the power 4. So delta cube y1 minus delta cube y0, this is delta to the power 4 y0. Similarly, you have delta to the power 4 y1. Next one is the fifth forward difference term, delta to the power 5. So delta to the power 4 y1 minus delta to the power 4 y0. This will give you delta to the power 5 y0. Do you have any further terms? No, right? Because if you were to calculate delta to the power 6, you should have at least 2 elements in the fifth column, but here you have only one element, so this is the end of the difference table. So if you note here, originally you have 6 data points and you have calculated up to fifth order difference term. So this is true for any case. If you have n data points, you will have to calculate difference terms up to n minus 1. So construction of the difference table is the basis for numerical interpolation, and in the next class you will see in the case of numerical differentiation also this is the first step. Now if you take the first diagonal row, the first term y0 is known as the leading term, and all these terms delta y0, delta square y0, delta q y0, etc. these are known as the leading difference. Identification of leading term and leading differences are very important, because when you do numerical interpolation, you are going to express the y values in terms of the leading terms as well as the leading differences. Okay. Now let's do one quick problem so that you get familiarized with the process of formulating the difference table. Construct a forward difference table for the following data. So x equal to 0.25, 0.26, 0.27, 2829, and these are the corresponding y values. First thing, just check whether the x values are equispaced. 0.26 minus 0.25, this is 0.01, and that is the constant difference between all the successive x values. So x values are equispaced. Now you can construct the difference table. Now how many data points do I have? 1, 2, 3, 4, 5, which means I have to construct difference term up to delta to the power 4. 5 minus 1, delta to the power 4. Okay. So I'm going to create a table with titles x, y, delta, delta square, delta q, delta to the power 4. X and y values are given in the problem, so I'm going to write down these values here. Now I can construct the first forward difference column. How do I do that? Simply calculate the difference between the successive y values. So 0.2571 minus 0.2474, this is the first forward difference term, 0.0097. Similarly, calculate the difference between these two terms, 0.2667 minus 0.2571, you get 0.0096. Similarly, find the difference between these two, you have all the first forward difference terms ready. Once you calculate the first forward difference term, you can calculate the second forward difference term. Simply calculate the difference between two successive first difference terms. So 0.0096 minus 0.0097, this is minus 0.001. Same way, find the difference between these two, you get the second one. The difference between these two, you have the third one. So you have calculated all the second forward difference term, you can move on to the third forward difference term. So the difference between these two terms, 0.0001 minus 0.0001. This is plus 0.002. Same way, find the difference between these two terms, you get the second term. So once you find the third forward difference terms, you can move on to the final column, which is the fourth forward difference term. So minus 0.002 minus 0.002. This is minus 0.004. So this is the last column. So this is very simple, right? This is very simple and straightforward. Just list out the x and values. Find out the difference between the successive y values, that will give you the first order. Then find the difference between the successive values in the first column, that will give you the second column, all the way to last column. In the last column you will have only one element. Okay. So as I said, this is the first step in numerical interpolation as well as numerical differentiation. This is very easy. Now let's see how to do this procedure using Python programming language. So specifically, I am going to construct a difference table for 4 data pairs. So this is a program which I have picked up from the reference book Computational Physics by Irinjalakuda. Let me admit that this is not a great program. The scope is very limited, but for the sake of simplicity or for the sake of accessibility, I have taken this from the reference book. Okay. So I have 4 data pairs. So I'm going to define the list first itself. The x values I'm going to call it as x data, y values I'm going to call as y data, and I'm going to initialize it as an empty list. Okay. Now I want to input the number of data pairs. In this case, I already know the number of data pairs, but for the sake of generality, I am going to call it as n equal to int input, enter the number of data sets. Okay, so the user is going to input the value 4 here. Now I have to input the values one by one. Since I have n data pairs, I need to invoke a loop having n number of iteration, which I am going to do using the range function for I in range n. So it will create a sequence starting from 0 all the way to n minus 1. So if you count, you have n number of elements here. I can input x and y values together using the split function. So x comma y equal to float x for x in input, enter x and y values dot split. Okay. As and when I input x and y values, I am going to append it or add it to the existing x data and y data. So x data dot append x, y data dot append y. So in that way, I have constructed x data and y data. In other words, the first 2 columns in these problems I have completed with this much of programming. Since I have 4 data pairs, I need to calculate difference terms up to 4 minus 1, which is 3. So I have to find out terms up to 3rd order difference. So the first difference terms, let me call it as list D1. Second difference term, call it as D2. Third difference term, this is list D3. So I am going to initialize this with a list of zeros. So D1, D2, D3, this is equal to 0 into n. So basically D1 will have n elements, all the elements are 0. D2 will have n elements, all the elements are 0. Similarly, D3 also will have n elements, all the elements are 0. So you basically start with all the elements being 0. Now you can modify all these elements. Okay. So first I need to print the first column, which is nothing but the x values. So you need to give the title x, which I'm going to give print \t x. So \t basically gives you a tab space. This is just for the column to appear good on the screen. You can print it without the tab space, but if you leave a tab space, it looks neat. So that's the only idea. Okay, so it's completely up to you. So this is the title. So once I give the title, I am going to print the x values one by one. For I in range n, print, I am going to use the formatted output. Once again, I am going to leave a tab space. So \t %6.3f. So this is completely arbitrary. The only meaning is that I am going to have 3 decimal points. It's completely up to you. You can leave 4, 5, 6, anything. Doesn't matter. Person x data I. So here each element of the list x data will be printed one by one. So the first column is printed. Now you have to print the second column. The title is y. So print /n/ty. So each print statement will print in a new line, but if you want to leave an extra space, extra vertical space or an extra gap, you can use the /n. So in that way, there will be a gap between the X column and the Y column. That's the only idea. So \n /ty, so the title is printer. Now you are going to print the Y values one by one. For I in range n, print \t %6.3f %y data I. So the second column also printed here. Now one thing, if you look at the problem, here X and Y columns are printed next to each other, but in this program, first all the X values are printed, under that the Y values are printed. That's the only difference between these two. Okay. So once you have X and Y values, you can calculate the difference terms. So the first forward difference terms D1. So let's give a title to it, diff1. So diff1 indicates the first difference term. So print \n /t diff1. Now you know that if you have n terms in your Y columns, the first forward difference column will have n minus 1 term. So your range function will have n minus 1 here instead of n. So for I in range n minus 1, how do you calculate the first difference? This is simply the difference between two successive Y values. So D1I equal to Y data I plus 1 minus Y data I. So once you determine the first difference term, you can print it, print \t %6.3f %d1 of I. So in this way, you print all the n minus 1 d1 terms. Next is the second difference column. You call it as diff2. So print \n \3 diff2. So the previous column had n minus 1 terms. This is going to have n minus 2 terms, right? One element less. So for I in range n minus 2, and you know how to calculate the second difference term. This is simply the difference between two successive first difference terms. So d2i equal to d1i plus 1 minus d1i. Then you print the d2i terms. Then you go to the third difference, which is your final column. Y. You originally had 4 data pairs, which means your final column is going to be delta q, or third difference term. So title is diff3. So here you are going to have one element less. So for I in range n minus 3. And d3 is nothing but the difference between two successive d2 terms. So d3i equal to d2i plus 1 minus d2i. Then you print the d3i terms. So you have printed all the difference terms one by one. Finally, you just say print n, just to indicate that the program is over. As I said in the beginning, this is not a great program. And this is the scope is very limited. Why? Because of two reasons. This is written specifically for 4 data pairs. For example, if you have 5 data pairs, then you will have to calculate diff4. You will have to add some more code to this existing program. Or if you have only 3 data pairs, you will have to eliminate this particular block. So the scope is limited. And the second limitation here, as I said, each column is printed under the previous column. If you look at this program, first you print all the X values, under that you print the Y values, then the first forward difference, second, third, etc. So if you want to display your data in the format shown here, then you will have to make some slight manipulations to this program, and that's going to be a homework for you. Display the table as shown in the previous program. Okay. So So you can make some minor changes to this program and get the output as displayed in the program. So do that as an assignment. So far we have talked only about forward difference. Let's also find out how to calculate the backward difference as well as the central difference term. So if you remember the definition, in forward difference, the first forward difference is calculated as the difference between two successive y values. So y1 minus y0 equal to delta y0. So if you look at the equation here, y0 is the leading term or the forward term. That's why the subscript corresponding to the forward term comes here. Similarly, the second term, y2 minus y1. So here y1 is the forward term. So the corresponding subscript will come here. That's why this is delta y1. Similarly, y3 minus y2. y2 is the forward term. This is delta y2. And the difference between two successive first difference term, that is the second difference term. So delta square y equal to delta y1 minus delta y0. Here delta y0 is the forward term, so the corresponding subscript will come here. So this is delta square y0. Similarly, delta square y1 minus delta square y0. Here delta square y0 is the forward term, the corresponding subscript will come here. So this is delta cube y0. Now, what about backward difference? The definition is exactly the same. The only difference is in the notation. So, delta is the forward difference operator, whereas del is the backward difference operator. So, the first backward difference is the difference between successive y values. So, y1 minus y0. Here, y0 is the forward term, y1 is the backward term, and the subscript of the backward term comes here. So del y1 is y1 minus y0. Similarly, the difference between next two y terms, y2 minus y1. Here y2 is the backward term, so the corresponding subscript will come here. So y2 minus y1 equal to del y2. Similarly, y3 minus y2 is going to be del y3. And the difference between two successive first difference terms will give you the second difference term. So delta y2 minus delta y1. Here delta y2 is the backward difference term, so the corresponding subscript will come here. So this is equal to delta square y2. Same way, delta square y3 minus delta square y2. Once again, delta square y3 is the backward term, corresponding subscript will come here. So delta cube y3 equal to delta square y3 minus delta square y2. Moving on to central difference, once again the definition is exactly the same, only difference is in the notation. The central difference operator is small delta, so y1 minus y0 equal to small delta y. So here you look at the central point or the midpoint. So the central point of 0 and 1 is 0.5 or 1 by 2. So the subscript is going to be 1 by 2. So delta y 1 by 2 equal to y1 minus y0. Similarly, y2 minus y1. The central point of 2 and 1 is 1.5 or 3 by 2. So this is equal to delta y 3 by 2. Same way, y3 minus y2. Central point of 3 and 2 is 2.5 or 5 by 2. So this is equal to delta y 5 by 2. Now you take the difference of successive first difference terms, that gives you the second difference term. So delta y 3 by 2 minus delta y 1 by 2. The central point of 3 by 2 and 1 by 2 is 1. So this is equal to delta square y1. So the next term is going to be delta y 5 by 2 minus delta y 3 by 2. The midpoint of 5 by 2 and 3.2 is 2. So the second term is going to be delta square y2. Now you find the the difference between successive second difference terms, that gives you the third difference term. So delta square y2 minus delta square y1. The central point of 2 and 1 is 1.5 or 3 by 2. So this is equal to delta cube y 3 by 2. So in all these cases, you can see the definition is the same, only there is a difference in notation. So that's for today. In the next class, we will see how to do numerical interpolation using a forward difference table. Thank you.